active learning for today. Passive learning. Okay, so we want to talk about relativistic gravity, and in the last section we talked about possible options that we can consider. We said that we want an exchange of a boson to be the cause for gravitational interaction, the boson to be the mediator, and we said that it seems that the simplest, the most natural option to consider is the massless scalar. So we want to continue that direction. That massless scalar field, sometimes it's called dilaton because it's supposed to couple universally to the trace of the stress energy tensor so that it has the right non-relativistic limit. So the action for the dilaton we said is this is a massless scalar field. So I write the following action. Just the kinetic term. This kappa I'll talk about it in a second. And then we want to copy it to the stress energy tensor of matter field. So there will be phi times T mu. So this is a valid interaction term that we can write because it's a Lorentz scalar. Now if we do the variation of this action, we get box phi plus kappa times T mu is equal to 0. That's the equation of motion that we get. And if we want to get the right non-relativistic limit, so remember that box is, in my signature box is minus t squared plus Laplacian, and this has to be equal to minus kappa T mu, and then in the non-relativistic limit the time derivatives are much smaller than the spatial derivative, so we get Laplacian phi on the left hand side. On the right hand side, the trace of the stress energy tensor will be dominated by the just 0,0 component of that, and that 0,0 component is dominated by the rest energy, so or rest mass. So what we get for this trace of T mu is just the mass density with a negative sign. So it becomes kappa times rho, which means that kappa has to be chosen to be 4 pi g, so that we recover the Poisson equation. Of course, once I write this action, and this T mu, let me emphasize, this is T mu for the other matter field. So if I want to write the full action, here I should write plus S matter, so there will be some matter fields in addition, or right, in addition to this phi, there will be some other matter fields that maybe I can just collect all of them inside some field that I call psi, and that T mu is supposed to be the T mu that I obtain using another procedure from this matter action. So, to be more precise here, I could put an index m, for instance, T mu of the matter field coming from the matter action. Of course, this is a linearized theory of gravity that I have written. As you see, phi only appears linearly here. There is no phi inside this T mu in the way that I defined it here, because I said I just derived it from this action. it's a valid question to ask what about the contribution of phi itself to the T mu nu. But that would be an effect which is higher order in phi. So at the linearized level, that would be neglected. Later we will talk about the nonlinear version of this theory and possibilities for including higher order phi. Alright, so now when we write this action, first of all, the simple calculation tells us how matter fits source phi, or also here. Of course, the action should tell us everything. So it also tells us how phi affects the motion of the matter field, so the evolution of matter field. In particular, we can use this action, and you are asked in the exercises, in the homework to do it, to see how, when you write this action for some simple case, say for instance this psi field is a massive field, massive scalar field for instance. See in some simple case that if you include this interaction, which will be a cubic interaction in this case, you will get a force between, you will get a non-trivial scattering between different matter fields. So for instance, if you have two species, psi 1 and psi 2, and they scatter through the exchange of this phi particle, then you see that there is a non-trivial scattering that can be, in the non-relativistic limit, it can be interpreted as having a force, the usual gravitational force between these sources. The usual, by usual I mean the Newtonian 1 over r squared force, or 1 over r potential. However, what we are going to do here is to consider the effect of this coupling to the dilator on the motion of a single particle. So remember we talked about the point particle that moves in the electromagnetic field, and how the effect of coupling to electromagnetic field can be included in the action. So we said that we have a point particle action for a couple of fields. So if we are in 4 space-time dimensions, it will be a function that depends on 4x mu's as the dynamical variables. And then we said that if this particle lives on some background field, then the coupling of the particle to the background field will be incorporated inside this action. So there was the term that would give us just the kinetic term, or could be thought of as the kinetic term, minus eta mu dx mu this sigma dx mu this sigma. And then in the case of the charged particle, we added a term coupling to a mu here. Now we want to add a coupling of this massive particle to the background phi field, right? Now we have a gravitational field. We know that gravity is universal. Everything which is massive is coupled to, or everything that has energy is in principle coupled to gravity. So we want to see how we couple this point particle to that phi field. And the rules of the game are right, the most general action that is compatible with symmetry. Here, since this phi is a scalar field, I can just add a function of phi here. Since I'm linearizing in phi, I can linearize that function and write 1 plus lambda phi. And that is a valid action, where at 0th order in phi reduces to what we had before for a free particle. Now we can ask, how does the addition of this extra coupling, how does it affect the motion of the particles? And by asking that effect, on the motion of the particle is the one that we expect in the non-relativistic limit, we are going to fix this lambda. So we do the usual thing. We vary this action with respect to x. Remember, this is the dynamical variable here. This is an action that is supposed to determine the motion of the particle. So we do a variation with respect to x, and we remember that this phi is also a function of x. Phi, we can be more explicit and write phi of x here. So when we do variation, we should also remember that there will be some pieces coming from there. So if we vary this, we get the following equation of motion. So there is a part that comes from the variation of the square root as before. So let's do it explicitly. And the sigma, the same as square root, minus eta mu nu dx mu d sigma d delta x nu d sigma times 1 plus lambda phi. So this is similar to what we had before, and then the second part comes from the variation of x in the argument of phi. So there will be plus the square root times lambda d mu of phi times delta x mu. And then we do a couple of integration by parts to capture the coefficient of delta x mu and require that to be 0 for the action to be stationary. And that gives us the equation of motion. So that will give us, this is an Opera factor, so we don't care. It gives us d by d sigma of 1 plus lambda phi eta mu nu dx mu by d sigma divided by this square root equals this is square root times lambda d mu phi. This is square root is the same as square root that we had before. And then we can take this as divide by the square root. Let's see, I did miss a sign here. You can divide by the square root and define the write it in terms of the proper time, d by d tau, which is this is square root. So the tau by d sigma is the square root of minus eta mu nu dx mu d sigma dx mu d sigma. So we divide by the square root and write the equation in terms of tau to get d by d tau of 1 plus lambda phi d eta mu nu dx mu d tau equals minus lambda d mu phi. So if I set phi to 0, I get the original equation for a free particle. Now we want to take the non-relativistic limit of this equation as before. Again, it's redundant. The zeroth component becomes redundant. We can just look at the ith component of this equation, which gives us and then in the non-relativistic limit, tau and t will be the same to leading order, so d by d tau is the same as d by dt. Dxi dt equals minus lambda di of phi. And to be consistent, I should also drop this phi on the left-hand side, because if there was no phi, I would have 0. Sorry, because the velocity is small, so there will be, if I act by the derivative on the phi, it is suppressed by the derivative. If I act on this, I will get a term which is suppressed compared to 1. So in both cases, I'm getting a subleading term. So in the non-relativistic limit, I will have dt squared equals minus lambda di of phi, and this is, if you remember that this phi is supposed to be a Newtonian potential, and we want to get the usual equation for a particle moving in a gravitational field in Newtonian physics, then you should set lambda to 1. Right, the force, the Newtonian force is just minus m times, let me write it using vectors, minus m times grad phi. So if I put m here and m here, I will get the Newton's equation with the right coupling. So we conclude that lambda has to be 1. We can also check that if we write this coupling with lambda equals 1, and we now look at it as a source for the phi field, it will agree with our choice of source being the trace of T mu nu. Again, just the consistency check. Any questions up to here?
Yeah. Why did you drop the lambda phi term?
In here, when I was taking, so there is a, let us keep track of it. So there is d2 xi dt square. If I keep it, there will be this times 1 plus lambda phi, and then there will be another term in which I take the derivative of phi. So this is d by dt acting on phi, which is going to be dxi by dt, so the sky velocity vi times, again there is a lambda and there is d phi dt, right? Now so first of all, let's first look at the first contribution. We are working at the lowest order in phi, right? And here we are already having a non-trivial answer if I set phi, if I ignore phi contributions. I get the acceleration, and then there will be a small contribution to that. But here I can ignore phi compared to the 1. You can also see from the equation itself that it tells you the acceleration itself is proportional to the gradient of phi. So the acceleration itself is something about the phi. But in any case, this lambda phi term is small compared to 1. So that's why I drop it here to leading order in phi. Here, it is a different term compared to that, but it is suppressed by the velocity, and now here I have a time derivative. Now this time derivative you should be a bit careful about. This is phi so if you remember here, phi phi is evaluated on the trajectory of the particle. So this d by dt of phi is actually the partial derivative plus the derivative because of the motion of the particle. So this d phi by dt is equal to dt of phi at constant x plus vi on the sky vj times dj of phi. Right. So now what we see is that both of these terms are suppressed in the non-relativistic limit. So there is a factor of v here, and then another factor of v here. So this is an order v squared correction. And this term is also an order v squared, really, because time derivatives are suppressed with respect to spatial derivatives in the non-relativistic limit. That's why we neglected phi on the right hand side. So this is also neglected. Other questions? Okay, so now let us verify that this action, when it is considered as a source for the dilaton, it agrees with what we wrote there, right? So we want this, when it starts out as a source, it will be the trace of the T mu nu of a point particle. So how do we do it? We first want to write this as in this form, which means that we want to write it as an action integrated over the full space-time. To do that, I just introduce a delta function. And of course, I just want to keep track of the second and the source term. So I will get minus m times integral d4x, and then there is another integral d sigma times this. But now we want to evaluate this x on the equation of motion. So now what I want to do is to think of it as a source for phi, but I don't care about the variation of x. So therefore, this part I can just write it as d tau. There is an integral over d tau. There is phi, and there is a delta function, delta 4 of x minus x mu, little x mu, which is the variable of integration, minus big x mu, which is the trajectory of the particle. So that's it. If I do this integral over d4x using a delta function, I recover this second term in here. So now if we vary with respect to phi, what do we obtain in the equation of motion? If we vary, or let us do it in a different way. Let me not vary with this. Let's just do it, work it out here. So we have plus d4x, and then there's this integral d tau m phi d4 x mu. What I can do is that to do the integration over tau using one of these 4 delta functions. So there is one of them which is delta of x0 minus x0, and if I want to do this integral, so let's write this as delta of x0 minus delta 3 of little vector x minus 3 vector x minus 3 vector big X. I want to do a tau integration using this delta function. That gives me, so this is equal to that, this is equal to d4x, m phi, I have it as before, delta 3 of the 3 vector x remains. But then when I do the integration over tau using this delta function, I get 1 over dx0 by d tau, which is, which if I multiply by m, both numerator and the denominator, this object that appears here is nothing but what we call P0, the zeroth component of the form momentum. So what we have obtained as the source is, so let me just rewrite this. What we have here is phi times m squared over P0 times delta of, and I again missed the minus sign, so there was a minus here, it disappeared here, minus here, minus there, delta of x minus x, right? And this big X is of course the trajectory of the particle. So we got this as the source, minus m squared over P0 times delta 3 of x on the trajectory of the particle. But this is exactly the trace of the stress energy tensor for a point particle. So if we derive the trace of if we derive T mu nu for a point particle, that is given by this expression. This can be verified very easily by doing the following. If I take the zeroth component of this, or zero mu component of this, and I integrate it over the whole space, remember the zeroth component, maybe I never said it explicitly, but you have probably heard it somewhere else, that the zeroth component of the conserved current is the density of a conserved charge. So if you integrate that zeroth component over the whole space, you should recover the conserved charge. So if you consider the 0 mu component of this T mu nu that I wrote here and integrate it over the whole space, you will discover the conserved charge for the point particle, which is the form moment of the particle. Okay, so this is the T mu nu for a point particle, and the trace of that is this in our signature. So this just checks with the original formula. That is. Any questions? So we have constructed the theory, a relativistic theory, that when we take the non-relativistic limit, it reduces to the Newtonian gravity. So this was just by construction. We constructed the theory to work like that. So if we want to see whether this is a viable theory to describe nature, to describe our world, we have to work on the non-relativistic predictions of this theory to see whether they agree with what we observe or not. By construction, it agrees with everything Newtonian. So this is relativistic situation or relativistic phenomena that we can consider in the theory of gravity. There are a few of them. So we are going to discuss some of them here. The first thing would be the redshift, gravitational redshift. Then we talk about the bending of light. There will be also the precession of the perihelion of Mercury that we don't talk about. But that's also something that could be a study for this theory, because it will give you some predictions or corrections on top of what you get in Newtonian gravity. And then there are gravitational waves, because this theory that we have written, it predicts the existence of waves. In this case, it will be dilaton waves. So these phi field, if you have particles that are moving, they will emit waves of this scalar field phi, and we have observed those both directly and indirectly, so we can check whether the predictions of this theory matches with them. Okay, so now we are going through this list, or some of the items in this list. The first one is the redshift. So what about the redshift? So we want to see if you have clocks inside some long wavelengths gravitational field, how the working of those clocks is affected by the field. So imagine the following situation. Let me just draw some space-time diagram. And suppose we have some time-independent gravitational field phi. So some phi of x for simplicity. And we have some observer who lives, or few observers who live at constant positions. Say Alice is at the origin. And then we have another, let me draw it closer. Another observer again at some constant position x. Bob is at some fixed position, and then they have clocks. They measure time, and there is this non-trivial field here. Maybe it goes to 0 at infinity, so some local field. And we want to see how the clocks in these two positions are related to each other. Or for instance, we can talk about biological clocks. So we can ask, for instance, how which one sees the other one dying first. And it would be, for instance, one way of doing this comparison is to consider some time intervals as measured by Alice, and think about some signals that are sent periodically or frequently at those intervals to Bob. So every 1 second, Alice sends some signal to Bob, and then Bob is measuring those, detecting those signals. and then he compares them with his own clock. They first agreed that the messages are gonna be sent every second. Then he receives them and sees whether they are arriving every second or driving slower or faster. So that's what we want to determine. So we have omega A and omega B. The questions are how they are related. Now, if the field is time independent, we have time translation invariance. So the time it takes for the signal to go from A to B will be independent of time. So all of these signals will take the same amount of time to go from A to B. Right? So if there is a delay, it's not because the travel time is going to change with time. There is one delay for every signal, but it's constant. So when you take the differences, it cancels. So in other words, we can ask the following easier question. What is delta t of these signals already here at the location of Alice, depending on omega A? And that delta t will be the same also here for both. Delta t is the coordinate time. So in other words, we want to understand what is the relation between delta t and the time that Alice measures, say delta tau for. Now, if this, so this question depends on how the working of clocks is affected by the gravitational field. And this is a bit dependent on the dynamics of clocks. For instance, if you have some clocks that work based on atomic transitions and put them in magnetic field, it's gonna change the frequencies. So the internal dynamics in principle can depend on this background field. But if it is gravity, we expect some universality of the result. So for instance, this coupling that we wrote here is supposed to apply to every particle. It's not selective, it's universal. So we expect for gravitational field to have some universality, and we want to see, for instance, if there is this universality that is dictated by this action with lambda equals 1, then what would it imply for the relation between the frequencies? So from this action, what we can see is that if we work in some other coordinate system called x tilde, where x tilde is given by 1 plus phi times x. So x tilde mu is given by 1 plus phi times x mu. Then in those coordinate systems, the action would look identical as before. We could also do the same check inside the action that we wrote for some field, for instance, where we coupled phi to t mu and nu. We could see that as long as phi is uniform, just a rescaling of the coordinate would get rid of that coupling that we have written. So in terms of these new coordinates, the clock should work normally. In other words, if Alice has if Alice has a clock that whose intrinsic frequency is given by omega A, for instance, if she goes to infinity with that clock, that would be the frequency that she would measure. When she comes to this position, it will still work for omega A, but that omega A would correspond to time intervals in terms of this tilde coordinate. Now we can translate this tilde coordinate to the original coordinate. So it is 1 plus phi A times delta x0 And remember, delta x0 is just this coordinate time. It's what I call delta t. Which remains invariant. So what we conclude is that omega a times 1 plus phi a has to be constant. For instance, if these signals are sent to infinity, then that constant is the frequency that I measure for these signals at infinity. That has to be omega infinity. So now, what do we see? We see that, now first of all, a question for you. What is the sign of phi? Is phi positive or negative? On Earth, for instance.
At the Earth, I think the frequency will be lower.
No, forget the frequency. The field, the gravity, the Newtonian potential. It's negative, right? It's an attractive potential. So it's the attractive potential is negative. So phi is negative. Therefore, when you go inside the gravitational field, the 1 plus phi is something less than 1. So what it means is that someone who is deep in the gravitational field and sending us signals, those signals arrive at us at the lower frequency, omega infinity, or the frequency that I observe those photons, they will be lower. So this is called the gravitational redshift. Since phi a is less than 0, it means that omega a is larger than omega infinity. One way to... Yeah.
Does it have lower bounds so we always get like a positive answer for frequency? Because if it was negative.
Oh, if phi becomes too negative, yes. Yeah, so then you should remember that here we were working at linear order in phi. So we are not allowed to consider values of phi which are of order 1 in absolute value. Now, if we want to consider those, then we have to construct a nonlinear theory. Now, the points at which this 1 plus phi becomes 0, they correspond to... Well, actually, when you go to a when you go to the nonlinear level, then before getting to this point, there is another point when 1 plus 2 phi is going to 0, and that point is where you have a horizon. So normally, I don't see anything beyond. But that is something that we should discuss only after building a nonlinear theory, which is valid for large values of phi. So one way to think about this redshift is that, so you're sending signals from inside the gravitational well. So you can think of this redshift. Remember we are talking about frequency, which is the energy of the photon. So what we are saying is that when we send this photon from deep inside the gravitational field, as they come out, the energy, the frequency has reduced, so the energy has reduced. So you can think of them as having lost some energy because they had to climb up the potential wave. So you have some potential wave here, and then your photons come out of that, but they lose energy. Any question? Okay, so let us discuss the bending of light, or bending of the trajectories inside the gravitational field. Now we want to consider again some localized time-independent gravitational field. Say we have sun, it has some gravitational field, it produces some phi here, d0 phi equal to 0, and the problem that we want to consider is that we want to consider some particle that is sent from infinity. So it's a scattering problem. The particle is sent at infinity when phi is equal to 0 with some energy, and some mass and some energy. And we want to understand or calculate for the trajectory of this particle in the weak field limit, meaning that we want to linearize in this phi. Okay, so let's go to the equation of motion for the particle that we derived before. So how did it look like? There was d by d tau 1 plus phi So let us first consider the mu equal to 0 component of this equation. If we look at the mu equal to 0 component of the equation, since the field that we are considering is time independent, we get a conservation law, we get a conserved quantity, which because the right hand side is 0, so we get that the left hand side is this object that appears on the left hand side is a constant of motion. So 1 plus phi times dx0 d tau is equal to constant. And that constant, I'm going to call it E divided by M. Because if we go to infinity, this constant is going to be, when we go to infinity, far away when phi is equal to 0, then we just get dx0 by d tau, which is energy of the particle divided by its rest mass. So it's the it's a valid identification. I can call this conserved quantity as energy. But now, as you see, this combination remains constant even when we come inside the field, when phi is non-trivial, because of the equation of the motion.
And what do we get for light?
What do we get for light?
Yeah, to consider.
Oh, you mean when there is no mass, when we consider massless particle? Okay, I haven't derived the equation of motion for a massless particle for you. So the trick to see what happens to light is to think about it physically in the following way. Consider what happens to a massive particle and then take the energy of the massive particle to be to infinity, to be much larger than mass. In other words, take your massive particle to be ultra-relativistic. Then by continuity, whatever happens to that ultra-relativistic particle should be the same as what happens to light. So that's what we are going to do. We want to see how the trajectory is going to depend on this ratio E over M. You could directly derive an equation of motion for the massless particle using a different version of this point particle action, which is called a Polyakov action. Because the action that we wrote, if you remember, there is an explicit factor of m behind it. So if you send m to infinity, it becomes degenerate. So either you can derive the equation of motion from this action and then take the limit of m to 0 together with the scaling of some other variable, which we might discuss later. So from that equation, we can derive the equation for massless particles. Or we can construct a different action that is equivalent to the original action that we wrote for massive particles, but there the mass equal to 0 limit is non-singular. So we can then directly derive the equation for massless particles.
And in the Polyakov action, we also get rid of the square roots.
We get, sorry, what?
Also get rid of the square root that we have in the point particle action that you wrote.
I've missed the first one. Did you get a scalar?
No, you get rid of the square root.
Oh, the square root, exactly, yeah. Yeah, there is no square root. It looks simpler. But it has a worksheet metric. So there is an additional degree of freedom. Alright, so let's continue. So we find the following conserved quantity along the trajectory. Now we go to the mu equals I, the spatial component of this equation. And we want to write that the spatial component in terms of time derivative rather than tau derivative. Well, because tau derivatives is not very good when we want to discuss massless particle. So we want to take that limit. While if we write it in terms of t derivative, that is just telling us how the trajectory is going to behave. So how one of the coordinates depends on the other one. So that is that's a well-defined way of parameterizing the curve. So I want to write it in terms of t derivatives. So I write dt by d tau, d by dt of 1 plus phi, then again dt by d tau, dxi by dt. And this is equal to minus di of phi. Now we use the fact that we use this expression. So remember, x0 is t. So this is 1 plus phi times dt times dt over dt is equal to e over m. So we use this to replace replace in the left hand side. So I get e over m 1 plus phi d by dt times e over m d by dt of xi equals minus di phi. Remember, e is a constant. Again, here I should drop that phi because I'm linearizing in phi. Yes?
Do we still have dt over d tau equals to gamma?
Say it again.
Do we still have dt over d tau equals to gamma?
Equals to gamma. Yeah, well, this tau is dt over this d tau is defined as before, right? So the d tau is, or d tau squared is just eta mu, or let's write it in coordinates. It's just dt squared minus dx squared. So yeah, if we divide by d tau, sorry, what do? We divide by dt squared both sides. So we get d tau by dt squared is equal to 1 minus v squared, or dt over d tau is equal to 1 over the square root of that, which is called gamma. Yeah, that is that.
But now we have to understand what is the meaning of t. It is the time coordinate used by an observer at infinity.
Yeah. Here is just our coordinate system that we are using. Now if we have observers who have clocks here, now we understand that what the clocks are measuring has some relation with t which depends on phi. But yeah, the coordinate t is just the usual Minkowski coordinate that we have. So what we see is that as I take the relativistic limit, meaning that you can keep m fixed, but send energy to infinity, or m over e to 0, to make the particle ultra-relativistic, then the equation of motion becomes the free equation. And therefore light, by the continuity argument, light decouples from the dilaton. It doesn't bend in the gravitational field. One other way that you could see this is to consider the coupling of phi to matter. Remember, we said that phi couples to matter via the trace of energy momentum tensor. So you have phi times t mu mu. Well, now you can ask what happens if we consider the trace of the trace for the Maxwell theory. and there it would recover, we will see that this trace is actually 0.
I have a question which is a little related to this one, but a little more advanced. We know that when we consider actions which are conformally invariant, then the trace is always 0 for the T mu. So can we say that if we consider any metric field which is conformally invariant action, then they will always be decoupled from the determinant field because the trace is 0?
Yeah, that's right. Other question?
I have a problem with this equation actually.
Which one? This one?
Because
What's wrong with
E over m is gamma, we know that it's gamma. And dt over d tau is gamma, so we get 1 plus y equals to 0.
No, E over m is gamma when you are at infinity. But now when you are inside the gravitational field, so let's remember how we discovered that E over m is gamma. Why did we call that? We derived it was basically essentially doing the same thing, except that you did it in the absence of the gravitational field. So we had a conserved quantity when there was no gravitational field, and that conserved quantity was dt over d tau, which is 1 over, what is it? Is it gamma or 1 over gamma? It's gamma. And then we concluded that the energy which is conserved is equal to m times gamma. But now inside the gravitational field, the conserved quantity is this object. In other words, let me say this in a different way. If you are uncomfortable with this equation, let's see, can we do that? Maybe we should do that. So you are happy that this is a constant, right? This is a constant of motion. No, I'm just saying that this constant of motion goes to infinity if you consider asymptotic particles which are more and more energetic. Because if I go asymptotically, we see that this constant is going to coincide with the energy over m. Okay, so let's see what we can do. One thing that we can do is to consider a metric description of this theory. So again, let us go back to this point particle action that we had. So it looks like minus m, this integral this sigma minus eta mu nu dx mu d sigma dx nu d sigma and 1 plus 5. So now one thing that I can do is to write this, introduce a metric G mu nu and write this as in this form, where the metric G mu nu is 1 plus 2 phi. Remember, I'm linearizing phi. So it's 1 plus 2 phi times eta mu nu. Of course, now this G mu nu depends on x, because phi depends on x. So we could do the variation of this action. Of course, we get the same answer, but it looks slightly different because now it will be written in terms of this G mu nu. So if we do that, then the equation that we are going to get is d by the sigma of G mu nu Now I'm going to, in a moment, I'm going to tell you what this d tau tilde is.
Looks like the geodesic equation.
Yes. So if I define the tau tilde squared in the same way that we define the Minkowski proper time, except that we replace the Minkowski metric by this G mu nu. So it's defined as dx mu, but with this G mu nu. Then that's how this equation, the equation of motion is gonna look. So now we can check that if we plug in this expression for G mu nu, we are going to recover the same answer as before. The same answer as what we had. Maybe this is an exercise for you. Now in here you can see that I can also define some for vector u mu tilde as dx mu divided by d tau tilde. And then this mu for velocity is normalized to 1, but with respect to this metric G mu nu. So now u tilde mu, u tilde nu times G mu nu is equal to -1. So for instance, this equation could also be written as d by d tau tilde of u tilde mu with lower index is equal to 1/2 d mu of g alpha beta u tilde alpha u tilde beta. So yeah, this is indeed called the geodesic equation for a particle that moves on some background metric, which is not constant. Now in particular here we have this background metric, and we get that equation that we had before. Now, one thing that we can do with this is that we can try to take this ultra-relativistic limit at the level of this equation to find an equation for a null geodesic, for a light part, for the light. So to do that is, so the trick there is that the problem there is that this, of course, this quantity is going to be 0, or this d tau tilde is ill-defined. It's not ill-defined, it's 0, so writing the derivatives with respect to tau tilde is not a valid thing. I should keep the expression in terms of sigma and do a rescaling of define sigma in a proper way. But we can try to do that. So if I write this in terms of sigma derivative, then I will have the sigma by d tau tilde divided by the sigma of g mu. So what happens is that this tau tilde goes to 0 and d tau tilde goes to 0 when we go to when we take the particle to be ultra-relativistic. So what we can do is that, or send the mass to 0. What we can do is that to multiply the equation by m squared and take the limit in the following way. Consider sending m to 0 but taking m times d sigma, d tilde to be a constant. So this is a particular definition of sigma, which is called which gives which is called the affine parametrization of the curve. So there is an infinite number of them depending on what constant we choose here. But the actual equation that we obtain is basically identical, except that tau tilde that we had here is replaced by this affine parameter sigma. So at the end of the day, the result is kind of trivial the same. Now, one important property of this geodesic equation is that if you have the metric which is independent of some coordinate, you get a conservation law, as we already saw in the particular example. So if the 0 of g alpha beta is equal to 0, then you get something is conserved, and that something which is conserved is u tilde 0. Right, because this equation, if you remember, this equation was d by the sigma of, let me write it in terms of the top thing, doesn't matter. Mu equals 1/2 d mu of g alpha beta u tilde alpha u tilde beta. So if I look at the mu component of this equation, if you look at 0 component of this equation and the metric is time independent, then I get a constant of motion which is u tilde 0. That's what we call energy before, maybe up to a sign, or E over M. So this is going to be constant. D0, G alpha, beta, C. This is also valid for null particle. So now, of course, I can also multiply this by M, and then this is nothing but P0 tilde equals constant. So this tells me that the zeroth component of the four momentum is a conserved quantity when it is written with lower index. The covariant component of covariant for momentum is zeroth component of covariant for momentum is a conserved quantity. Now, for instance, we could ask about this example of redshift. Remember, one way of talking about redshift would be to consider a photon and see what is what frequency different observers measure for the photon. So if you remember, we said that the frequency which an observer measures for a photon, we can write an invariant relation for that. So for instance, an observer Alice is measuring the frequency of the photon that is given by the four velocity. Now we consider this four velocity, u mu. And then we contract that with the four momentum of the photon, k mu. So that is a frame-independent expression for the frequency of the photon measured by an observer. Now, if I have an observer at rest and I want to use this normalization condition, observer at rest means that I is equal to 0. There is only zeros component of this. So we should have G00 times U tilde 0 squared is equal to -1. And then we use our definition of G mu nu in the particular case of the dilaton field to get U tilde 0 equals 1 over 1 plus phi and 0. Remember again, we are linearizing phi. So 1 over 1 plus phi is the same as 1 minus. On the other hand, K, so this expression therefore is U tilde 0 minus U tilde 0 times K0, but K0 is a conserved quantity, so we can identify with the frequency of the photon at infinity. To be more precise, minus the frequency of the photon at infinity. So this becomes U tilde 0 times omega infinity of the photon. So we get omega infinity divided by 1 plus phi a, which is the same result that we had before. We can also see why the light doesn't bend in this theory, because now here if we consider again our dilaton gravity theory, then d mu g alpha beta is actually proportional to g alpha beta, because the metric is of this form. So this d mu g alpha beta is just twice d mu phi times G alpha beta is, again, remember we are linearizing phi, so it wouldn't matter if I write G alpha beta or eta alpha beta in this case. So this is in the direct and gravity case, I have d mu phi times G alpha beta, but then it is contracted with the four velocity of the geodesic. But for a null geodesic, this is equal to 0. So that's how null geodesics decouple from the from this this theory. Questions?